Imagine an assembly line at peak capacity when a robotic welding arm suddenly slams against its own chassis, sending sparks across the floor. Unplanned downtime cost manufacturers an average of $260,000 an hour. While maintenance teams typically look for mechanical fatigue or sensor failure, a different kind of disruption, the digital command injection, can mimic a hardware breakdown while bypassing every physical safety check. For decades, industrial security was defined by implicit trust. If a device was physically located inside the factory walls, the network treated it as a known, safe entity with total access to the system. This wall-based security becomes a liability when factories integrate cloud computing. Once the machinery is connected to the outside world, the assumption that internal equals safe provides a direct path for attackers. The Purdue model uses isolated layers to keep the outside world away from the Level 1 controllers driving the assembly line. But modern IoT connections pierce through these layers to reach the cloud, removing the isolation this architecture was designed to provide. Connecting these older architectures to the internet transforms high-speed efficiency protocols into accessible entry points for external threats. The protocols governing these machines were never built with security in mind. Modbus TCP, for instance, dates back to 1979, a time when uptime and low latency were the only priorities and authentication didn't exist. This allows an attacker on the network to send a raw payload, like a function code 06 command, directly to a controller. Because it doesn't check who is sending the command, it accepts instructions to rewrite holding registers, changing motor speeds or temperature limits instantly. Newer protocols like OPC UA and MQTT offer security features, but they are often deployed with protections disabled to reduce processing load. Without encryption, the factory's internal telemetry is broadcast in plain text. Any node on the network can see the JSON payloads containing sensitive thresholds and operational limits. Since the machinery can no longer be protected by a physical wall or the protocols themselves, the network must transition to a zero-trust model. The first pillar of this transition is mutual TLS, or mTLS. It replaces open, plain-text broadcasts with a cryptographically encrypted data stream. During an mTLS handshake, both the gateway and the server must prove their identities using digital certificates before the connection is established. Data only moves once both sides are verified. The second pillar is deep packet inspection, eliminating open networks. An inline firewall examines the intent of each packet. It allows standard read commands to pass, but blocks unauthorized write commands, even if the source appears local. These two pillars ensure that every device is verified and every command is inspected before it can affect the physical machinery. The final challenge is connecting the factory floor to cloud services without introducing a single point of failure. Storing permanent, hard-coded API keys on factory hardware is a significant security risk. If one gateway is compromised, an attacker can use those stored credentials to access the broader cloud. Workload Identity Federation removes this risk by using short-lived tokens. The gateway uses its digital certificate to request a token that expires after 60 minutes, providing a temporary, secure connection. By removing permanent passwords from the hardware, you ensure that a breach of a single device cannot escalate into a full-scale cloud compromise. When mTLS encryption, edge microsegmentation, and identity federation work together, they create a cohesive security layer. As shown in this blueprint, this architecture creates a secured pipeline for telemetry, protecting the data from the moment it leaves the controller until it reaches the cloud analytics dashboard. This framework allows manufacturers to utilize cloud-based AI and predictive maintenance while maintaining the safety of their physical operations. In a landscape where digital commands have physical consequences, the assumption of implicit trust is no longer viable. To utilize the predictive power and efficiency of the cloud, manufacturers must first build their factory networks on the foundation of zero trust.